Hi, my name is Colin Parker, and I'm going to be talking about predicting success of a Freedom of Information Act request using deep learning and natural language processing. The dataset is just over 19,000 federal FOIA requests, with the text of the request explaining what the request is asking for, alongside metadata such as the request agency and date time of submission. It was collected from the Muckrock API, which is an investigative journalism site that focuses on government transparency. After collection, the data was pre-processed using tokenization followed by TF-IDF vectorization of entire documents for the simpler models and glove word embeddings for the recurrent neural network models. So a request can be completed, rejected, or accepted, but no relevant documents found. Predicting this final result is a multi-class classification problem. And there are some challenges associated with it, such as a mild class imbalance and also overfitting. We have millions of parameters for the more heavyweight models training on only thousands of requests. And finally, neural networks don't handle categorical data such as request agency as well in general, and more heavyweight models like LSTM and BERT can't accept metadata at all. On the left, you can see an embedded view of our vectorized dataset, and it seems difficult to draw a decision boundary between these three classes. Two of the simplest things we can do are, number one, to predict the majority class for everything, and number two, to draw an artificial decision boundary that perfectly categorizes the training data. So on the left, we have predicting that every request is completed, an accuracy of about 41%, but this F1 score, which is a weighted measurement across the different classes that punishes incorrect predictions, and particularly punishes treating these classes unequally, is very low. On the right-hand side, our accuracy is lower, but our F1 score is higher, but it seems as though we're essentially randomly predicting the test data set for our overfit model. So the simpler machine learning models that I used first, softmax, k-nearest neighbors, random forest, and gradient boosted forest, handled the metadata well. They don't treat it any differently from the TF-IDF vectors. The gradient boosted forest algorithm LightGBM performed the best in cross-validation, so I used this on top of all of my deep learning models to incorporate the metadata. In the graph at the left, you can see our LightGBM model starting to separate the data as desired. Here we have two deep learning models which have different drawbacks. On the left, the sequential model is over-predicting the majority class, while on the right, the LSTM appears to be clustering its output into more than 3 clusters. Neither of these vanilla models outperforms the tuned gradient boosted forest model, so we'll move on to a one-dimensional convolutional neural network model. So here, words are embedded using the glove vectors and processed in groups of 3, 4, and 5 to extract features from groups of neighboring words. As I mentioned before, the penultimate layer is piped into a LightGBM model to incorporate the metadata, and this outperforms all the previous models. You can see visually it does a better job at sorting the different data types into 3 distinct clusters. But our very best performing model is the most state-of-the-art and most heavyweight model, a BERT sequence classifier with over 13 million parameters. It incorporates information of a word's position in the text, which segment it belongs to, which are separated by commas and periods, and it incorporates attention masking. Multiple avenues of transfer learning were attempted with BERT, but the most effective was fine-tuning the entire model using a low learning rate. The F1 score and accuracy and validation were the highest of all the models I considered, but because of the size of this model, I actually chose to deploy the CNN-based model, the previous model, in my web application. So how can these models be improved even further? Firstly, by gathering more data or augmenting the training set we already have, using translation to a different language and back, or replacing synonyms at random, or swapping or deleting words at random, we can augment our training set. And specifically for the BERT model, we can pre-train it on similar tasks, such as maybe the state and local FOIA requests or other government form classification. I've included links here if you'd like to learn more, ask me a question about this project, or talk data science in general. Thanks so much for your time.